Today we're going to be looking at some problems to review for the Unit 3 test. So the Unit 3 test will be divided into two parts. Let's take a look at some of the problems you might see on part 1. So what is the domain and range of this graph? What are the domain and range? How do we find those? Pause the video, see if you can come up with the answers, and then resume the video, see if we get the same ones. So we're going to start over here. Remember, the domain is our valid x values. So we're looking at the x-axis here. We're looking to see which x values exist for this function. So we see that it starts here at 4. It goes over to the right and it keeps going. It has an arrow, so we have an arrow going to the right. And then we have everything in between, so we can draw a line in between them. And then we just need to write what that interval is. Our lower bound is -4. Our upper bound is infinity because we have an arrow. Our lower bound is a closed dot, so then we have a closed bracket, square bracket. And we always use a round bracket for infinities because we can't ever possibly get to infinity to include it. So that is our domain here, -4 to positive infinity. Now how about our range? We're looking at y values for our range. So let's see, where on the y-axis does this function exist? Let's see, it looks like our bottom value is 0. And then it goes up, 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 and looks like it has an arrow here, so it's still going up. It looks like it's going to the right faster, but it is going up, 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 still up forever. So that means we also have an arrow going up. And now we have a line in between these two dots. Draw a line this way maybe. So a line going from the dot at 0 to the arrow above. So now our lower bound will be 0. Our upper bound is positive infinity again. We have a closed dot at 0 for a square bracket. And we always use a round bracket for infinities. So that's how we find domain and range on a graph. Now we're looking for minimum and maximum in a table. How do we find the minimum and maximum values in a table? Well, let's see, we could look at x values, or we could look at y values, or we could look at both. Which apply for min and max? So another way to think of this is the min and the max are the top, or the bottom and the top of the graph. And that's why we have a graph here. We could graph these points and just look and see which ones are the bottom and the top values. So if we graph these, -2, 9 goes there, -1, 7 is here. We have 0, -1, which is here, and then 1, 0. Now it's pretty easy to see where our top value and our bottom value is, right? There's our top value at 9, and here's our bottom value at -1. So the top value is 9, the bottom value is -1. That's our maximum and our minimum. Now if you don't want to graph these points, you can notice we took those two values from the y values. Our biggest y value is our maximum. Our smallest y value is our minimum. That corresponds to these y values, the top and the bottom y values on the graph. Now let's look at our next problem. Which of these graphs are functions? How do we tell functions? We have the vertical line test, right? So if we draw a vertical line anywhere on the graph, it should only go through one time. So is this first one a function? It is. Go ahead and pause the video and go through the rest of these, and then come back and see if we get the same answers. This next one is not a function because it goes through twice. Third one here, also not a function. Any circle will not be a function because it will always have a place, it will have many places where vertical lines pass through twice. How about down here? Is this a function? Let's see, we can do vertical lines, those all pass through once. Those all pass through once. It looks like this gets pretty steep, so if it ever got perfectly vertical, then it would hit this line twice, but it doesn't look like it ever goes completely vertical. So really, if we just keep drawing vertical lines here and here, it will still only go through once. This is a function. This one is not a function, goes through twice. And our last problem over here, looks like we have some vertical asymptotes, indicated by these dotted lines. If we do, oops, that's not really a vertical line. If we do the vertical line test anywhere on this function, any of these three sections, you'll see that it only passes through once. This is indeed a function. We notice here with these asymptotes, this is going to get closer and closer and closer and closer and closer to this line, but never quite cross it. So we know that this never quite goes vertical for sure, because it's approaching an asymptote. All right, next problem. We have a graph, and we need to find out what f of 1 is. F of 1. So how do we find that? Well, we know that our notation here is f of x, so 1 must be our x value. Let's go on our x-axis. Here's our x-axis to find 1. Here's 1. And now we need to go match that up to the function. Where does the function exist for 1? That's right here. So our y value is -1. Our x value is 1 and our y value is -1. That's what we're looking for in this problem. -1 is our answer. Remember, f of x is going to be asking for our y value. Our y value is -1 in this problem. All right, how about f of -2? Same idea. This is our x. -2 is our x. We're going to take our x-axis, go over to -1, -2, go up to the function. Here's where it matches the function, and our y value here is 5. So our answer here is 5. All right, now let's look at two functions graphed against each other. This graph models two pools being drained. That might be familiar from one of our recent lessons. And they intersect at the point 10, 14,000. So here's that point where they intersect 10, 14,000. You might notice the units on this graph. We have time in minutes and gallons of water as we're draining the pool. And it asks, what does this intersection mean in context? What does this point right here represent? Well, we know that this indicates 10 minutes, right? 10 minutes, and then 14,000 gallons of water. So at 10 minutes, they both have 14,000 gallons of water. They have the same amount of water at that time. At 10 minutes, both pools have 14,000 gallons of water. So they have the same amount of water. That's what an intersection means here, because we're measuring the amount of water. All right, part 2. Here are some problems you might encounter in part 2 of the test. Similar types of problems. This graph shows Mandy's journey home. X is the time in minutes and Y is the distance in meters. You can see here we have the x-axis, time in minutes. Here's the y-axis, distance in meters. And then we have a function shown. And they're asking us for several different features of this function and then an interpretation of the x-intercept. So let's look at the domain. What are our valid x values? That's our domain, valid x values. So we drop this down here. Looks like it goes all the way over to here, and then we have all the values in between. So we write that as an interval, lower bound, upper bound, closed dot, closed dot. Remember, the square brackets mean we include that point, so a closed dot corresponds to a square bracket. Now how about the valid y values? Where are valid y values on this graph? Well, it looks like the bottom value is right here, so the bottom value is 0. And our top value, let's see, we go up to here, but it keeps going up. This is our top value of the whole graph. That goes up to here. And all the points in between exist, so we're going to draw a line here. And our range, the lower bound is 0, the upper bound is 1, 2, 3, 4. So lower bound, upper bound, filled in dot, filled in dot. Okay, I'm going to erase these now so that we can draw a little bit more on this graph. The intervals of increase. Where on this graph is it going up? Well, let's see. It looks like it's going up here, and then it stops and it starts going down. So where does that correspond in time? At what time is this graph going up? Let's see. It starts here, and it ends there, and it's all the values in between. So this is an interval again. Our lower bound is 0, our upper bound is 4, and we have closed dots. How about intervals of decrease? Well, it's going to be these other spots on the graph where it's going down. So where does that begin? Looks like that begins here, and it ends over here. And it's going to include everything in between. So we start at 4. 4 is our lower bound right here. 4. And our upper bound is 10. So from 4 to 10 is our interval of decrease. And we have closed dots, so those are going to be square brackets. And finally, what does the x-intercept mean in context? So what is the x-intercept, first of all, and then what does it mean in the story? The x-intercept is where our function crosses the x-axis, right there. Looks like it's at 10 minutes. The y value is going to be 0. So what does 10 minutes mean in this story? What happens at 10 minutes? Well, let's see. Mandy's x is the time and y is the distance from Mandy's home. So if it got to 0, that must mean Mandy got home. So at 10 minutes, Mandy got home. That's the interpretation of our x-intercept. What about our y-intercept? They didn't ask for this, but what if we wanted to interpret the y-intercept right there? What would that mean? This is 0 minutes, right? 0 minutes and there's a certain distance from home. So this would be where Mandy started. Because She's been traveling for 0 minutes. All right, next problem. Complete the operation g of x plus f of x equals h of x. Oh, this looks complicated. Is it going to be complicated? Let's find out. G of x plus f of x equals h of x. So we're adding a function to another function. And we need to find the equation for h of x. How do we find that? If we add this one plus this one. Well, it turns out we can actually just add them like we would add anything else. Add numbers and we just combine like terms. So g of x plus f of x, we said that's h of x. And notice how these are color-coded. They're color-coded by like terms. So this is an x term and this is an x term, and we can combine those. 12 plus 14.5 is going to be 26.5, and it will have x as its term. Now these ones are also like terms. These are numbers that we can combine. 200 plus 425 is going to be 625. And that's our answer. H of x is this equation, 26.5x plus 625. So it's not too complicated, actually. We just add both of the functions together. Exactly what they told us to do. We just add them. And our last problem. What vertical shift can be performed on g of x to get f of x? So here we have g of x, a blue line. And then f of x is a red line. Looks like it's below g of x. What do we need to do to g of x to get it to be f of x? Now, Y-intercept, your Y-intercept might be a really good place to look at this when you're shifting a function vertically. If we watch what happens to the Y-intercept, let's see, we started here, we go down 1, 2, 3, 4, 5, 6. And notice we're counting the whole numbers, not just the lines. The lines are half numbers. So we counted 6 down. That's actually our answer. We went down 6 to get from g of x to f of x. Let's count that one more time. 1, 2, 3, 4, 5, 6. Now if we wanted to write that in algebra terms or on an equation, that would be subtract 6. Or another way to think of that is 2, we start at 2, minus 6 is going to be negative 4. 2 minus 6 equals negative 4. So both of these answers are correct ways to answer this. Both of these indicate a vertical shift. And that wraps up everything for our Unit 3 review today.